And we are live.
Hello.
Good morning, evening, afternoon, whatever it happens to be for you guys. Thank you for coming. Please take a minute to post your country and your name and introduce yourselves. We are all eager to see you. What are the odds that the first two people to say something are both going to be from Lima, Peru?
Yeah, wow.
California?
I've been to Lima. It's cool.
Germany, Connecticut, New Hampshire, Ontario,
Oh,
Venus.
Berkeley. I'm in Berkeley. Hi, let's see, who said that? Michael, I'm in Berkeley.
Southwest Missouri, Finland, and SLU is the group. I remember now.
Yeah. India, all right. Spain, UK, Ohio, Albuquerque.
San Clemente, Central Florida. Ooh. Wow. Sorry, so many I can't keep track.
More Spain. Awesome. These webinars are popular.
Yeah.
Oh, Vallejo. That's near where I'm at.
Cool. Okay.
Oh, Barbados. Cool.
Slovenian sounds very Dr. Seuss-esque.
Yes, it does. I was just thinking the same thing. All right, well, it is 11 o'clock.
Yep. Let me go ahead and share my screen real quick, and we can get started. And then I have to make this into slideshow view. Oops, I have the webinar over the top of it, so I can't actually. There we go. Hello, everybody, and welcome to the first of two site and equipment webinars that we will be having to close out our very successful Observing Section webinar series. This one will focus on, well, it won't really focus. It's going to tell you as many things as you can possibly want to know about the intricacies of the different ways that you can get involved with the with site and equipment and all of the different possibilities that exist there. Obviously, it won't be all of the different possibilities, but it will at least cover quite a few of the highlights. The first thing that I'd like to do is give a big thanks to our sponsors, Boyce Astro, and their Initiative and Education Foundation. Boyce Astro provides online education, astronomy education, observatory resources, and research experience to students, student teams, and schools to learn how to perform observations, conduct research, and publish their results in scientific journals. And they have been a close partner and ally of the AAVSO for several years at this point. We would also like to thank ADIC Cameras. They manufacture a diverse range of quality astrophotography cameras and accessories, along with a free range of software to help you maximize the output of your equipment. For more information, you can visit their web pages. As always, there will be links to those in the post-webinar email that you will receive. Just a few highlights about the webinar series itself, rather just a few bookkeeping notes. The chat will be located here. Most of you have already found it. You can ask a question through Q&A. Please ask your questions here as we can easily scroll through them. Sometimes they are very difficult to find in the chat. If you have any sound issues, your best bet is to go here. Hopefully there will be something here that will help you with your audio settings. There isn't much that we can control on our end. So hopefully you can figure that out. And without further ado, I will send it off to Richard Berry to introduce the Site and Equipment Observing section.
Thank you, Bert. The sections for many, many years did not include the instruments and equipment that we use. They were focused almost entirely on the object we observed. And yet there was a continuous and ongoing need to talk about instrumentation and to talk about the equipment. So at, I think sometime earlier this year, they said, we need somebody to take that over. And I finally said, okay, I'll do it, having no idea what I was getting into, but thinking, you know, it might be fun. And it has been fun. Our section now covers, we called it instrumentation because I'm now talking about things that measure stuff, and equipment, which is things that do stuff, like telescope mounts, whereas instruments will be more like cameras and stuff like that. Today's group, we put together to present a diverse picture of what the section is all about. We'll begin with Molly Wakeling talking about how a photographer became a photometrist. Okay, and I think there's probably a lot of beginners out there who are thinking, I don't know if I can do that. Well, Molly will talk about how to do that. Photometric filters by Phil Sullivan. Astronomers like to use filters so that they know what wavelengths we're looking at. Phil will fill you in on that. One of the fundamentals in understanding how your camera works, whether it's CCD or CMOS, is characterizing it. What's the gain? So forth. Is it linear? Timothy Wakeling will be talking about that. One of the most fascinating areas is Astromakers. You can build your own equipment, like a really, really great flat fielder. So George, Alan, Aaron, Helmer will be talking about that. And we'll be wrapping up with Tom Smith talking about observatories. Hopefully everything from the very simple thing you can put in your backyard, like a tarp over a pile of 2x4 frame, all the way through to something really, really fancy. And then there will be question and answer at the end. So without further ado, I will turn it over to Molly.
Good morning, everyone. I'm just going to go ahead and hop into my presentation here because that's where I have my introduction and whatnot. All right, there we go. Okay. I've been doing astrophotography for about the last 5 years, and I have been wanting to do scientific observing for a while. So I'm going to talk about in this presentation how I used equipment that I already had and the similarities and differences between doing astrophotography and scientific data taking. So first, a little background on me. I have my bachelor's in physics from Washington State University, and I got to spend 3 summers working at the Lawrence Livermore National Lab, where I got to do a lot of hands-on experiment and stuff like that. So I love messing around with hardware and learned a lot about sensors and detectors and stuff like that. So it's got me a lot into working on the hardware side of things. Currently working on my PhD at UC Berkeley, doing neutrino experiment stuff. And I do a lot of STEM outreach as well. I like to do a lot of stuff with scouts and star parties and astronomy club events and things like that. On the astrophotography front, I started out with an 8-inch Cassegrain on an Altaz mount with the DSLR, and my equipment and knowledge base have grown quite a lot since then. And I've been able to do all kinds of different astrophotography and get really into it. I just joined the AAVSO back in October after meeting Stella Kafka through a mutual friend. And so that's kind of how I learned about how I can do some of the scientific data taking. On the astrophotography front, I've taken a lot of data over the last 5 years, 92 unique deep sky objects consisting of 292 data sets. I oftentimes go back and re-image stuff as I have better gear and better skills, which is over 500 hours of astrophotography data. So a lot of messing around with gear and processing and stuff like that. And that's just the deep sky objects. That doesn't include AAVSO or solar system data. But I've been wanting to get into doing some kind of scientific measurement type stuff for a while, and learned about variable stars and exoplanet measurements and things like that from various people in AAVSO and other organizations. So let me go through what my current setup is right now of various bits and pieces that I pulled together from my collection of telescopes. So I have the capability of setting up in my backyard, which is really awesome. I live just north of Berkeley, and my skies are about Bortle 7, which makes things difficult for astrophotography, and makes some of the really dim stars hard to access, but isn't really much of a showstopper for doing variable star observing, with a camera at least. I have an 8-inch f4 Vixen Newtonian that was a gift from an astro friend of mine in my previous astronomy club, who is kind of passing on his gear to up-and-comers. I have this old, kind of crappy Orion Deep Space Monochrome Imager 2, which is a CCD camera with a 16-bit ADC, which is nice. Although the camera has kind of some issues, and I'll probably end up replacing it at some point. But it's a camera that somebody gave me at some point that I pulled out of a box. I'm like, hey, I can use this for scientific data taking. I have yet to characterize it, so I'm looking forward to seeing that portion of today's webinar to learn how to do that. There's been some kind of quirks with it I'd like to sort out. The mount is a Celestron CGE Pro, which is really kind of overkill for this application, but it's a mount that I already had that is semi-broken. The declination axis motor has some issues, and it doesn't auto guide, but it will track and still does go to, so there is that. But now the RA motor is starting to have some trouble too. It's Celestron mount, there's all kinds of problems. I have a filter wheel that actually works very well in Starlight Express, and I have a 7-position 1.25-inch carousel in there right now. And another gift from another astro friend in the same astronomy club was a set of Schuler Johnson Cousins BVRI filters. I don't have the U filter, but I have found that most people aren't as interested in U as in the other channels. And I didn't know what they were at first. He didn't know what they were. I posted on Cloudy Nights about them, and somebody was like, oh, those are photometric filters. You want to sell them to me? I'm like, no, those sound really cool. I'm going to hold on to those. And now I've been able to use them. So that's been really neat. I know Astrodon sells some as well. But yeah, they'll be coming up later in the webinar about what these filters are. And I have an electronic focuser so that I can have good focus between the different filters and with temperature changes and whatnot. And I'm not auto guiding at the moment. My deck axis won't auto guide, but I could at least guide the RA axis, but now it's having trouble too. So I might just not guide this one. We'll see. Okay, so what is the difference between what I call pretty picture astrophotography and variable star / exoplanet observing? So for pretty picture astrophotography, there's a lot of things that you need in order to make a picture look nice. You want nice round stars. If your stars kind of start to streak out a little bit, become elongated, it makes your image look messy, and usually I throw those frames out. You want to have as low noise as possible, and we use cooled cameras and lots of processing to process out that noise. And one of the things to help reduce that noise is taking many hours of exposures. A lot of post-processing is involved, getting good at using PixInsight and tools like that. Having dark, clear, transparent, moonless skies are really what you want to use for astrophotography. High quality optics, a mount that works really well. But in my experience so far with doing variable star observing, pretty much none of that is necessary to be able to take reasonable observations. So your stars don't have to be round. They just need to be round enough to be able to plate solve. You know, if they're really streaked out, the plate solver is not going to be able to figure out what part of the sky you're looking at. And it can cause some difficulty in processing, but they don't have to be really round. Having low noise is not super important because you stack a couple of frames and you're still able to integrate over the size of that star and get a brightness measurement with that noise present. Instead of spending hours on a target, I spend a couple of minutes on a target, especially for one that's not like a time series over the course of the night. If I'm just taking one observation that night, I'll take 5 frames in each filter, and that takes about 5-10 minutes, and that's about it. And then I move on to the next target. So you don't need a ton of data on a given target to submit that data. Processing is much quicker and easier. There's not a whole lot that you have to do. You can shoot through a full moon, through light pollution, through haze, because whatever effects like haze or extra light and stuff like that are on your target star are also on your comparison stars. So the levels relative to each other are still the same, which is the important bit. So you can image in less than ideal conditions. Maybe, and if you only have one rig, you can spend the less ideal nights doing variable star observing and the more ideal nights doing pretty picture astrophotography. You don't need as high quality of optics. That Vixen Newtonian, like many Newtonians, has some pretty severe coma. And I'm not even using a coma corrector. I can't quite get the spacing figured out, but the camera I have has a very small chip. So I don't even see the coma, but even if I did, having the stars be a little bit elongated is not a problem. And you don't necessarily need an equatorial mount either, because if you're using, if you're only doing 5 or 10 minutes on a target, you're not going to get a whole lot of field rotation. And if your star that you're interested in is in the middle, then you don't have to worry about it being cut out by the field rotation. And you don't need a mount that tracks super duper well. You could use lesser equipment and be able to get good measurements still. So to kind of see the differences in what those data sets look like between astrophotography and variable star observing, here's just a quick example. On the left is a single frame on the top and then a fully processed image of the Pleiades cluster. And that's almost 6 hours of data with a really nice refractor and lots of processing. And over on the right, the top is a single frame. The bottom is a stacked and inverted frame in the VPhoto software. It's 3 minutes of exposure time using a photometric filter. And it's on 11th magnitude star and I still got a really high SNR, even though this camera is relatively noisy. So just to kind of give a visual on what the difference between those two images looks like. So how bad can your data be and still give a reasonable result? So these are some less than ideal examples that I still processed and submitted data for. So the one on the left is bad tracking. You can see my stars are elongated. Maybe not the most precise of measurements as far as the fact that the annuli are circular, doesn't quite match the star, but the error was still pretty low on that one. The middle one, it was a it's a noisy image. The transparency was poor, but despite that, it was still, I could still see that 11th magnitude star. That one's Tabby star right there. And the comp star is well enough to get a measurement. And if you actually might want to be a little bit out of focus from what people tell me, like the one on the right, because then you have more pixels over which that star is, and you can not be as susceptible to individual pixel difference in levels and stuff like that. So it's a little bit out of focus, and that actually probably helped make that a better measurement. Okay, so to kind of, when we had Stella Kafka on the Astro Imaging channel recently talking about AAVSO and how to submit data. And I think a lot of people were pretty mystified by how you actually process the data and what that whole process looks like. So I'm not gonna go into detail on how to use VPhoto because of time limitations, and there's manuals out there for that. But I just wanna kind of do an overview of what that process looks like, just to kind of demystify what all is involved. So just like regular astrophotography, you still want to take darks, you need to take darks, and you need to take flats in order to have a more accurate measurement. And I calibrate my light frames in PixInsight still. You can use whatever software you already use for doing the calibration. And you need to save it out as a 16-bit FITS file because VPhoto doesn't like 32-bit for some reason. But you don't want to do any other processing on it, just calibrate. And then upload those FITS files to VPhoto. And you can actually do that as a single zip file, and it pulls all the relevant information out of the header. I have to specify which filter it is because I call them different names than their standard names. But yeah, that's all the information I have to provide it is what telescope I used and the filter I used, because all the rest of the information's in the header. Then I stack the images in VPhoto because that way it preserves the timing information, which is important for knowing the air mass and some other things that it uses to calculate the magnitude of the star. So here I have several IR filter images on TCRB, and I stack them in VPhoto, which is really just an average. It just averages them. And then the next is the calculation steps. So you click on that stacked image and you click on variable star index or GCVS, and it's already plate solved your images. So it goes through and highlights those stars for you. And then you delete all the stars that you're not currently interested in making a measurement on. And then also have it's got a list of comparison stars for all the variable stars that are in the database. So it will find those for you. You don't have to go through and identify which star is which or anything like that. And then you just a couple other parameters to get a good measurement on the size of the annuli and things like that. There's details on that in the manual. And then you check to make sure that the error is low and none of the comp stars are far away from their true values so that you know you have a good measurement. And then you hit the generate report button and it spits out a text file that you then upload to WebOps. And that's the whole thing. Probably takes about 20 minutes. And that's your submitted observation. And you have done science. You've contributed to the scientific community. Your data shows up in the light curve generator on AAVSO, and people who are doing research on variable stars can download those data sets, and your data is a part of it. And every week you get a summary email on which of your data sets have been downloaded. So it's really cool to know that you've participated in the advancement of science and getting to participate in that. I get to do it in both professional and an amateur capacity, doing two different kinds of things. But yes, you have contributed to the doing of science. And I guess we're going to do questions at the end. So but you can go ahead and throw the questions in the Q&A so that you don't forget them. And if you want to follow my adventures and misadventures, I am on social media as Astronomolly Images, and I'm on Astrobin as Molecule, or my observer code is WMOB. And yep, thank you.
Thanks, Molly. Next up, we have Phil, who's going to be talking about photometric filters.
Okay, my name is Phil Sullivan. I've been a member of the AVSO for quite a while. I do observations from my own observatory, and I also use the AVSO network telescopes, and I also teach photometry in the choice courses. My discussion is going to be primarily directed at people who are transitioning from astrophotography to photometry, and also for beginners. I don't have time to do everything I want to do, so I'm going to refer you to a spot where I had an extensive post. See if I can find that slide. There we go. If you want the basics, go here. I'm going to leave this up. Put my notes there. I'm not really familiar with all the technicalities here. This is a link to a forum post where I kind of condensed all the things I thought were important for really beginners. And I'll leave that up for a while. I really want to get to 3 basic issues with filters. There's been a lot of going on with filters recently, and not all of it is good. The first question is, do you really need to buy these filters? And for a lot of people, I think the answer is no, at least for beginners. As you get more experience and you get more experience, you're eventually going to want to get photometric filters. But for starters, if you have a RGB set, you can use the green. Green works very well as a substitute for the photometric V. If you look at the transmission curves for V and G, they're very, very close. Now, so you can get your experience and get started using the G filter, and you can do good quality of photometry with the G filter. The only problem with using a G filter, you have to limit your targets to what I call non-red stars. Probably something with a B minus V of 1 or less. If you use non-red stars, you do very well. Eventually, there's a process you can do called transforming your G filter to V filter, but that's something that's more advanced, and I don't think I really want to get into that. But there may be more discussions about that in the forums. The real goal is just get started. Start using your G filter as if it were a V filter. Start getting practice. Submit your measurements to the AVSO. You're only going to know how well you're doing when you can compare your own measurements with other people's measurements. So submit your data. If you're using a G filter, you have to identify your filter as TG, and then see how you're doing. And don't be worried about it if you submit something that doesn't look quite right or looks really, really bad, because it's very easy to remove what you think is a bad data point without any fuss. Okay, so there are also a few things you can do without using a filter at all, but I don't have time to get into that. What I want to cover next is what you need to know to make an intelligent decision about buying filters. There's 2 basic ways to make these photometric filters. I'm going to be referring only to the Johnson-Cousins photometric filters. There's 2 ways to do it. You can make them out of a colored glass where the photons you don't want it to come through are absorbed by the light, or you can do it by multiple optical coatings where the interference effect causes, gives you the filter effect. This is, is everybody able to see this? Johnson-Cousins filter. Okay, well, I'm going to screen share here. Is that showing up?
You'll need to stop your screen share and do the thing where you select your desktop instead of the single window.
Oh, stop screen share. Okay, here I am again. Now let's go screen share again.
Yeah, and then hit that first icon that says desktop.
Okay. Here's what I want to show. So there now?
Yeah.
Okay. Okay, these are the transmission curves for the Johnson-Cousins filters. U, B, V, R, and I. Notice a couple of things. Notice how close and how much overlap there is between the V and the R. Also, the peak transmission is pretty close in the B and V. There's less overlap, and there's more distance between the peak. This is I. The maximum response to most silicon detectors, CMOS and CCD, is in the R. Notice this little bump down here. This is the blue filter, and a little bit of sensitivity all the way into R. We may end up having to talk about that a little bit later, but that could be an important thing. Okay. So there's another kind of filter, the series of filters that you need to see. Is it showing up?
So I think when you shared your screen this time, you clicked on this particular image, so you'll have to stop sharing again and switch over.
Okay, good, thank you. Stop sharing. Okay, screen share again.
Yeah, or just hit your whole desktop, then you don't have to do the start stop thing. Or that.
Is this showing up?
Yes.
Okay, so these are the Astrodon Sloan filters. Now, these are mostly used by professionals, but you should notice that have a very different pattern than the Johnson-Cousins filters. They have these vertical sides and a very flat top. This is a hallmark of the Sloan filters, and also of you can only do this with interference filters. Okay. Now I'm going to have to tell you make a very bold statement, is that I think that the Astrodon filters are the best. And these are the ones that have been used the most for a long period of time in the AAVSO. And I've done some testing recently, and the Astrodons still are, in my opinion, the best. Recently, however, actually about 3 years ago, Astrodon was bought out by another company and called Optical Structures. It also bought out a bunch of other small amateur astronomy sites like Lumicon, JMI, Farpoint. After this happened, the Astrodon filter started drying up. The access was getting difficult. And actually, at one point, Astrodon stopped producing filters completely. There was no production from Astrodon. Now, recently, they're starting to come back again. And this is very promising, because a lot of people thought that Astrodon, the best filter maker, was going to go under. But now people are starting to get them again. But you have to understand that if you're going to order Astrodon filters, you're going to have a long wait measured in months. I'm going to talk a little bit about the Bader filters. These are made in Germany. They have a good reputation. They are actually made as a combination of the colored glass filters and coatings. But the problem with the Baders now is that they're going to stop making them. They put it on their site that there's no more going to be making new Johnson color filters. They're going to switch over to the Sloan filters. So this is a consideration. If you want to get the Bader filters, you better buy them soon, because when the stocks are gone, they're not making any more. The Bader filters are 5 millimeters thick. This is pretty unusual. Most Bessel filters are the colored glass filters are called Bessel filters, and they're generally 4 millimeters thick, and the interference filters are 3 millimeters most of the time. It'd be very nice if you had your filters all the same thickness, because then you don't have to refocus between filters. Recently, some so-called Bessel filters, that is, Bessel means colored glass filters, started showing up under a couple of different brand names. But the problem is, if you look at the transmission curves, they're not. I'm going to stop and start again here. Okay. Now here are we seeing this? Okay. This is the transmission curves of these new so-called Bessel filters. Here it says right here, Bessel photometric, UBVRI, interference coatings. This is an oxymoron. Bessel filters are colored glass filters. But these have shown up under a couple of different names recently. Okay, so I'm going to say more about this a little bit later. The also new like optolongs. Optolongs, I think, have been around for a while for astrophotographers, and I know that there are filters that are used by people who do exoplanet observing, but they're new into the photometry market. So I did some testing on these filters myself. I tested my own Astrodons versus the optolongs and the chromas, which are some of these new so-called Bessel filters. And based on my testing, the Astrodons were superior. These so-called Bessel filters didn't do very well, and the optolongs did pretty well. So I think optolongs are a good option. I think these Bessel filters, so-called Bessel filters, need some more work, and I don't think they should be called Bessel. These should be called Bessel filters. So next thing I wanted to cover is if you're going to buy filters now, which ones should you consider? And I think it depends on your situation. If you don't have any filters at all, and you really want to get into photometry with photometric filters, then I'd recommend the optolongs. They seem to be decent filters, and they are much cheaper than the other filters. Look around, though. The retailers are selling these different prices. Most retailers will give you the lowest price that they can, if you can prove that the low price came from a reputable dealer. When you buy the optolongs, you can only buy full sets. This includes a U filter. I thought this was probably not a great idea because as Molly said, you're really not going to use the U filter. the atmosphere and glass absorbs the U signal, and the only thing that you can use it for actually is, I think, observing Venus. That's the only thing that's bright enough to use a U filter for. And one of the retailers I talked to said that, yeah, if you buy the optical lens, you get the U filter, you can actually sell the U filter to the pretty picture people who want to take pictures of Venus. Now, if your situation is that you have the red, green, blue filters, I suggest you just use the green filter for a while, get your experience there, and let the dust settle, because there's a lot of strange things happening in this market now. But if you think you're going to really be serious about photometry, you might consider putting in an order for the astrodons. You at least want a B and V and maybe an I. And just realize you're going to be waiting a couple of months at least.
Oh, you got about 2 minutes left.
Okay, but if you don't order direct, but I would recommend that you don't order from a dealer, who's going to charge your credit card to keep your place in line. One of them is going to do that. And you might be taking a risk because it's not for sure that Astrodon is going to survive. But I really want Astrodon to survive, so I want people to order the Astrodons because they make the best filters. And if we don't have Astrodon, it could be a very sad case. So if you have a batter filter, if you have a batter V, you better start scrambling to get a batter V and maybe an I, because batter is also going out of the filter business, the photometric filter business. They're gonna, if you can still get them, the batters are good filters, I think, and you'll have a fine set, but you might lose your opportunity. So the cautions, I would avoid the mislabeled Bessel filters. Be careful of anything that's sold as a UBVRI filter as Bessel. You have to check the transmission curves. If it looks like this, I'd keep away from it. If it looks like this one over here, anybody see that? Can't see that?
We're still seeing your Bessel photometric slide.
Let me start this again here. See that?
Yeah.
If you have these typical Johnson-Cousins filters and they say it's a curves and they say it's a photometric Bessel filter, you're probably fine. That is a true Bessel filter. If it's got those flat tops and steep vertical sides, it's not. It's one of these pseudo-Bessel filters. The problem with those is that in my testing, they don't do very well, and they're the most expensive filters out there, even more than the Astrodons. Okay, so I hope that's helped. A lot of people have been asking questions about what the filters are, what filters to get, and this market is in flux, in chaos, really. But I hope to make some decisions. Okay, that's it.
Thank you, Phil. Next up, we have Tim Weaver talking about camera characterization. And if you don't mind stopping your screen share, Phil.
Oh, I'm sorry. There we go.
No worries. Take it away, Tim. I think you're muted. You are unmuted, but I cannot hear you.
His microphone might be muted separate from Zoom. Looks like he's looking at it. No, we still don't have you. What? Make sure that there's not a hardware switch on your mic, and also make sure that it's not muted on your computer, like if you're on Windows or, yeah. No, we still don't have you. You could also, in Zoom, make sure you have that microphone selected. Okay. He's gonna go out and come back, I think.
I think I heard some sound. I'll give him 1 more minute, and if not, then we'll just move on and come back to him.
Okay, Astromakers are standing by.
Yeah. Since I'm not 100% sure what's up with them, why don't we give him a couple minutes to figure it out? Alan, do you mind starting up the Astromakers presentation?
Let me start.
All right,
Let me give the
George,
introduction.
sorry. I wasn't quite sure who was going first.
Okay, so if let's see, I'm shared and on the screen. Excellent. So Astromakers, what are they? Now, the Astromakers is the part of the instrumentation focus group, which is focused on making things. This builds from the whole maker movement, which you may be familiar with, which is the umbrella term for independent inventors and designers and tinkerers, a convergence of computer hackers and traditional artisans. Remember Heathkit and the Radio Shack kits? Well, this is, nowadays we have things like Adafruit and SparkFun and all these other places for buying parts and in building projects. So in our goal in the Astromakers is to really bring projects forward all the way to the point of where other people can build them. If it's a hardware project, we're going to publish schematics and bill of materials and instructions on how to build. And if it's software, the software is going to end up in a repo, so everybody can take a look at it, modify it, and tweak it. But rather than doing a more general talk, let me turn it over to Alan Slisky, who's actually building some projects, and after that, Helmar Adler, who's also building a real project. Let's take a look at what they're doing. Alan, why don't you jump in there?
Sure. I'm an astromaker since before it was called that. I've been making astronomy gear since I was in high school or before to chase eclipses and stuff. And I'm getting much more back into it lately, helping some friends and colleagues build equipment for observatories, large and small. And it occurred to me that a lot of the development effort is common to what other people need, and there's no reason to not share it all. So with Richard Berry's help and Arnie Hendon's help and George's help, we're trying to disseminate some of this information so that other people can bootstrap off of it. So we have a lot of the underlying technology in pretty reasonable shape, and if other people want to take on some of this work and build some stuff for their own observatory, that's a good thing. We have more people doing it. Several of these gadgets, I'm gonna stick to calling them gadgets for a while, have common application, and many times there are good commercial solutions, and sometimes there are not. And people can build this stuff either because they're interested in building their own stuff, because they want to save money, or because they want to customize it somehow to their own needs. And those are all valid. And there are people that want to buy a working solution and get on with their observing, and that's fine too. We have a very open system. So I'm going to talk about some of the gadgets I've been working on, and I'm working with George and Arnie to put these things into a format that other people can pick up and work with. So the picture you see is a large telescope I've been working on out in New Mexico. It's a 36-inch Bowler and Chivens that was at Princeton. It was given to a friend of mine, and we built a new observatory in Mayhill, New Mexico, next to New Mexico skies. And it's pretty much all back together, and it's almost ready for remote autonomous observing. You can see the telescope, but the thing on the wall, the white dot with the black surround, is a interesting combination of ideas that I've been working on for many years, and Arnie Hendon has also been working on. So it's a combination of technologies that is ready for other people to use. So the mission is to design gadgets for astronomical observatories and to use the existing ASCOM standards so that we can communicate with the world. All the high-level applications, ACP for observatory automation, and Maxim and things like that. So all of these widgets have a common language. They speak a common language. There's a recurring need for these functional instruments to automate a remote observatory. You need weather information, you need a flat fielder, you might need a focuser or a filter wheel. There are some good ones on the market. There are many marginal ones on the market. And I get requests from people to build equipment that can't be bought. So to make a flat fielding system for a 36-inch telescope, there's nothing you can just order. So we're going to try to generalize that to allow you all to make your own stuff, whether it's for a 80mm refractor or something much bigger, where sometimes a custom solution is necessary. And we're going to adopt the open source model so that we can share with people this information in a way that they can pick it up and run with it. Open source, I have an interest in the history of technology, and the open source movement, I'm going to say, started in Massachusetts and actually up and down the Connecticut River Valley in the mid 1800s. The first rifles with interchangeable parts was made in Windsor, Vermont. The Springfield Arsenal in Springfield, Massachusetts played a big role when the Arsenal contracted out parts to be made by local machine shops. Part of the deal was you had to show the government inspectors how you made the stuff. And that's sort of, I believe, sort of one of the early examples of open source. The machinists used to travel from shop to shop and work for each other, and the ideas would spread. And their attitude was this open source thing, where it's good to share knowledge. And if you built a very cool machine to make gun stocks or something, I could buy your machine and I could take it apart and say, oh, I can do that better. I can make a new machine, and nobody would shoot me for that. So in that spirit, these astronomy gadgets, I've made the executive decision to choose a couple of common elements, the box and the board. So I finally found a very nice weatherproof plastic enclosure that'll hold an Arduino board. Now, if you want to design your own 3D printed enclosure, you're welcome to do that. If you want to recompile the code to run on your vintage PDP-8, you can do that too. But I want to provide at least one working example. These are some of the functions we're looking at: weather safety system, flat field illuminator, an observatory roof open close. A real dome controller is much more complicated. Maybe we'll get to that someday. Focuser, and maybe a filter wheel controller. ASCOM standards, if you're not familiar with that, there's a wonderful ecosystem for common language for astronomy gadgets, cameras, filter wheels, weather stations, things like that, and it allows a common interface. There's a relatively new feature of that called ASCOM Remote, and they've branded this new thing, they call it Alpaca, and what it is, it's a way to have network devices. The older model of having a device driver in the computer vanishes, and now the device that's on the network, again, speaks this common language for the device that it is. I'm very happy that they've made that move. I've been urging lots of people for years to go to Ethernet instead of USB or serial ports, even worse. Part of it is that USB and serial ports go directly to your motherboard, and astronomical observatories often are in places where they have a lot of lightning, and that's a bad combination. And ASCOM also, there's a big infrastructure. So if you develop something, there's compliance testers, simulators, and there's a big ecosystem and network of support. The first gadget that I thought might be useful very generally is a weather, I call it a weather safety system. You can call it other things, but you need to understand the local conditions to decide when and if to open and close an observatory remotely, even if it's just in your backyard or if it's across the world. And the only very local conditions that you need to know about are rain and clouds. If you want to get the wind speed and the temperature, whatever, you can fetch that from nearby weather stations that people graciously connect to the internet. And having a record of cloud cover for the evening may help you check your image quality. And the rain sensors and the cloud sensors basically don't open if it's raining and close if it starts raining. So here's the CAD model of a very simple gadget. It has an Arduino board and a rain sensor in a box. I've chosen, for several reasons, I'm not going to get into a lot of detail, but an Arduino Mega. Arduino is a very popular microcontroller for hobbyists, and they're readily available. They're not very expensive. This particular version has Ethernet integrated, and more importantly, power over Ethernet. So you don't need a separate power connection to the box. You can run the standard power over Ethernet, so you have one cable to the box. I found this very nice optical rain sensor. So the electronics is not actually out in the weather. You know, there are a lot of conductive type rain sensors, and they do work, but they're actually exposed to the elements. So somebody makes this little gadget. It's about $50, and it has a little heater in it, and it has the electronics, and it uses the internal reflections in this acrylic dome to see whether there's raindrops on the surface. Uh,
Alan.
is a infrared sensor that's sold to the Arduino community, the hobbyist community. It's $3 or something. It's not very expensive. It looks at the sky, and you can tell whether or not it's cloudy. If it's cloudy, the sky is warmer than if you're just staring out into deep space. It also has a ambient temperature sensor built in so that you can check the local condition, and the code is readily available and it's easy to integrate. So I designed a box. This is part of what will be available. So you can buy that particular plastic box and you can follow these plans and drill the holes in the right place and be able to build the gadget. And here it is together with the Arduino in the box. This thing on the left bottom is a waterproof Ethernet feed through. So it allows you to get the Ethernet cable in without getting the insides wet. And then the rain sensor cable comes around and talks to the Arduino. The details of this, we've built 2 or 3 of those so far, and the documentation needs to be polished up. It's not, we have a couple of early adopters that aren't afraid of, this is not Heathkit that was mentioned before. In the 60s and 70s, people would make either simple things or the major project. You could make you could assemble your own color TV. And they had tremendously detailed instruction manuals. If you want an interesting example, go on eBay and buy an unbuilt Heathkit. They're getting pricey now, but anyway, fantastically detailed. I don't intend to do that. So you have to have some skills and have a little bit of a sense of humor to take on a project like this, but it's doable. And what I want to do is provide an example, at least one example where it all works. And then people can either build that and move on to the next thing, or if they want to fiddle with it and add a ultraviolet sensor, that's okay too. So what I expect will be, the project will be a description of what's going on, a bill of materials, which is a parts list, and where to get all the parts, mechanical drawings like you saw of the box, where to drill the holes, the Arduino code, and some build instructions so that you have an idea how to put it together. So that little plastic box, you need to tap the holes in the bottom of the box to accept screws to mount the Arduino. Not hard, but it's just a note. Flat field illuminator is the next thing. That's fairly far along. Same box, same Arduino, and much of the code will be the same. And I've designed a printed circuit board that can run up to 4 LED channels and has a stepper motor driver if you want to motorize cover. So there is a new device type for ASCOM called the cover calibrator. It's a motorized lens cap with the flat fielder built in. There's a commercial product called the Flip Flat. I don't know if they're making them anymore, but same idea. But it turns out there are some other applications. So you can make a flat field illumination panel. I'll show you that in a minute. This color calibrator, which would have the motorized lens cap with the flat fielder built in. You can use the same stuff for testing camera linearity, because you have very precise control over the illumination levels. And then Arnie mentioned that there might be interest in a visual photometer. And the hardware would be, an eyepiece holder with a beam splitter of some source and optics to create an artificial star. But this circuit and everything could be used to drive the LED with a range of known brightnesses.
Just a
So
reminder, over time now, Alan, so you might want to wrap it up.
Yep. So this is the circuit board that drives the LEDs and the stepper motor. Okay, and this is talking a little bit about the flat field illuminator. So I've discovered these broadband white LEDs that match the sky pretty well. And you can also have UV and infrared LEDs and 16-bit pulse width modulated control. These are the filter transmissions I measure. This is the zenith sky spectrum on the same scale, different times before and after sunset to compare to doing sky flats. These are the white LED spectra. This is installing those white LEDs on the front of the 36-inch telescope. And that's the flat panel. It's a styrofoam panel, which is very inexpensive, and styrofoam is very white, not because of the composition, but because of the structure. The foam creates this white like snow, and you don't have spectral features. It makes a good flat field panel. And it's illuminated by the ring. What we found is if you put this panel one radius away from the ring, you get extremely good uniformity. We measured the uniformity very carefully with a calibrated light meter. And this is the cover calibrator I'm working on. This is the CAD model, open and closed. You can see the LED array inside the cover. And here's the project status. There's some code, which is kind of the major element left to be done. The weather box needs, I got to update the documentation. The flat field illuminator needs to be packaged up for people to test out. The calibrator is not quite ready for release. Roof controllers, others not begun. Anyway, I encourage you guys to participate. And there's an AVSO forum for this stuff that's just getting organized. Thank you for your attention.
Thanks, Alan. So let's try Tim again. You just muted yourself.
I'm sorry, can you hear me now?
Yes, yeah, we can hear you. Perfect.
Okay, yeah, I apologize I tested this equipment out when I first got it. I thought it was going to work out. So let's get started.
Sounds fine now, so.
All right, let's get started with I'm jumping way ahead. There we go. All right, CCD and CMOS and linearity. Now, linearity is very important for taking accurate measurements of stars. Linearity simply means that the proportion that the amount of time that the amount of light that you gather is proportional to your ADU count. If the light you gather if you double the amount of light you gather, you double your ADU count. When there's no direct relationship between the light gathered and ADU count, the relationship is nonlinear. All right, before we start on linearity, I'm going to talk a little bit how CCD and CMOS cameras work. All right, if you've ever looked close up to your screen of your television or your computer monitor, you know there's like little cells inside. Those cells are pixels. Well, just as your television has pixels, so does your camera, or at least your electronic camera does. And what these cameras do is that whenever they're photosensitive semiconductors, basically. Light, a quantum of light falls on a pixel. And a certain percent of them are absorbed into the semiconductor material. It loosens up an electron, and the electrons are gathered in something that's roughly a capacitor. And this happens during the entire exposure time. When the exposure time for the image is over, then all of those electrons are then shifted or moved to an amplifier where they're measured and stored as an analog to digital unit, which is the ADU. Now, the difference between CCD and CMOS is that CCDs have like one or two of these amplifiers that are ADU that measures the electrons or the analog output. Whereas each of those CMOSs, each of them have their own amplifiers and they measure them out. So you can so think of it as a CCD as a series, more like a series circuit, whereas the CMOS is more like a parallel. And you can guess which one probably is going to be faster than the other. And I have I have an animation I can show you. I just have to stop sharing for a second. Okay, can you see it? Okay. As you can see, okay, it's real quick. I tried to look for a longer video, but basically, the CMOSs with the CCD, all of them collect and they read out one row at a time, right here on the electron to voltage conversion, right there. Whereas with the CMOS, they read out on each individual pixel. Okay. Now with analog digital conversion, okay, the way your information is stored, everything is stored as basically as zeros and ones. And the more resolution or the more brightness resolution that you get out of your camera, the amount depends on how many of those zeros and ones you have to store that information in. Sometimes you have 12 bits. Sometimes or at least with a lot of the CMOS cameras, you have 12 bit, and some of them are some of the DSLRs are 14 bit, but a lot of your astronomy CCDs are 16 bit. So with a 12 bit, you can store values from 0 to 4095. For 16 bit, you can store from 0 to 65,535. This is not really a measurement of intensity, but it measures the units between. It's more of a resolution. The best analogy would be having something that measures in feet versus something that measures in inches. Like if you had a measuring tape that only measures in feet. So if you measure somebody's height, okay, if they're 5'4", all you can measure them is at 5 feet or 6 feet. So you can either round up or round down or round to the nearest foot. You don't get you don't really get an accurate measure with them. On the other hand, if you have a measuring tape that you can measure in inches, you can get down to 5'4" or 5'7" or 6'3". And your 12-bit would be the measuring tape that only measure in feet, whereas the CCD, the 16-bit camera, would be the one that measures in inches. Now, whenever you submit your data to AAVSO, it's all going to be in 16-bit. Now, that doesn't now how do you get 12 bits out of a 16-bit camera? Well, all it does is just multiply that value, that analog digital unit, by 16. So you go from a 12-bit to 16-bit, but it's not really that accurate. The equivalent would be to take the tape measure that measures only in feet and then multiply by 12. You won't get any, and it won't be any more accurate. Instead, what you'll have is a bunch of people that's going to be measured in 60 inches and 72 inches and 48 inches. So all you've done is take the foot and multiply it by 12 to get inches. Now, here's some of the factors that affect linearity. All right, full well capacity. This is the amount. This is actual measure of intensity, or how much intensity you can measure. All right, whenever your CCD camera, what it measures is electrons, basically. The photons are just all right, it's supposed to be measuring photons, but your analog digital unit is measuring the electrons that you get from whenever the photons hit the pixel. So the larger the full well capacity, the more photons you can store. I mean, the more electrons you can store. And this is usually in proportion to the size of the pixel. Bigger pixels will hold more electrons. And here you see a chart showing pixel size, all measured in microns or 1/1000th of a millimeter to show how small they are. And it can go all the way up to 24 by 24 microns. Now, most of your regular CCD and CMOS cameras are going to measure in the range of 10,000 to 100,000 electrons for each of those pixels. Though there is the exception, the Apogee Alpha F6. That's an example of one that can hold up to like 500,000, but that's because the pixels are you can actually hold at least a dozen pixels in one of their pixels from even one of the cameras for one of the larger pixels. Now CCDs have something known. Now there are some CCD cameras that can hold twice as many pixels than a comparable camera with the same. They can hold the same amount of electrons. They can store the same amount of electrons in their pixels as a comparable CCD camera. And the reason why is there is something called an anti-blooming gate. What happens is whenever that pixel becomes saturated, if you don't have an anti-blooming gate, then the electrons will bleed over to the pixel next over. Now you may seem like, well, we don't want that one because it's going to just mess up the image that we take. It's going to bleed over into that next star over. But the advantage to a CCD camera with a non-anti-blooming gate is it has greater linearity and it can store twice as many pixels. You just have to be careful not to oversaturate your pixel. Now, some manufacturers, they will give you a lowball estimate on the full well capability of a camera. The reason why that is linearity. Their camera is linear up to a certain point, and then everything becomes nonlinear. So what they do is they give you the full well. The camera can actually hold more pixels, but then it would start being nonlinear. Quantum efficiency. This is just this is how efficient your CCD camera can absorb photons. You have a certain percentage of your photons that will actually be absorbed by the CCD camera, and others they're not going to read on there. Now you'll get a certain you get a plain flat number for it, like one of mine, the ones that I'm going to show you later, which I did the linearity test on. They give an 80% quantum efficiency, but that 80% really is for one wavelength of one wavelength of light. Over other wavelengths, it's not as efficient. So it'd probably be more accurate if they were to integrate the quantum efficiency across the entire wavelength. At least it is to me. It would be a more accurate measurement, but they don't do it that way. So you have to be careful with that. All right, determining linearity. Okay, I took pretty much a bare bone approach to that. And what I did was the same thing you do with taking flat frames. The speaker before me was talking about taking flat frames. Flat frames is just a way of dealing with the uneven collection of light in a telescope mirror or lens. So if you can see this picture right here, the light is not evenly distributed. And there is some variation in the light, particularly in the corners. The corners look real dark. That is known as the netting. And to correct for that, you take flat frames, and the flat frames will calibrate your images to correct for that uneven distribution of the light. It's also good for detecting also for calibrating for dust particles that would wind up on your CCD sensor or on the filter as well. Okay, so what you do is you use what I use is a light box or a flat box, and what I do is I take the image and I take the image until it's until it averages at 1/3 full well depth. So whenever the image averages out at about 1/3 of the I guess the ADU count, that would be the amount of exposure I would have for that picture, for that image. And then I would average out all the all the flat frames, because I would take about like 15 of them. And this is
2 minutes left.
Okay, this is my light box right here. Okay, this is something I made at home. And all I would do is, since I have a uniform source of light, all I have to do is vary the exposure time. And this is for a ZWO ASI 183 monochrome camera. The time is measured in milliseconds, and I measured out the average ADU count after it's been converted to a 16-bit image. And you see it's pretty much a straight line, right? And I didn't just take one image. I took 10 exposures. I took 10 images, each at an interval of 1 millisecond in exposure. So I took a set of 10 at 1 millisecond, a set of 10 at 2 milliseconds, so on, averaged them out, and I plotted them on the graph. All right, and here's my sites. Here's some of my sources that here's some of my sources that I use for this presentation. All right, okay, I'm done. Unless you got any questions.
Yeah, thanks. Next up, we actually have a final addition to the Astromakers section, which is Helmar.
Thanks, Bert. Hello, everybody. Let me share the screen. Can you see the screen on your end? Okay, I would like actually to follow up on what Alan gave before his talk before. I was asked to talk a little bit about what I'm doing. We have independently worked on what we sometimes call a weather box. So again, that is a safety gadget to make sure that our telescopes are not getting rained on, or that we can take images which are not obstructed by clouds, for example. So for a long time, I was thinking about what I should be talking about. I don't want to duplicate what other people have done already. So I called this here New Tools, New Fun. We are at an age right now where the Internet of Things is exploding. There are a lot of open source software solutions around which we should be utilizing. There is a lot of hardware developed which we could be using. It's getting cheaper and cheaper and more powerful. So what I would like to give you is a very brief introduction into some of the possibilities we have in regard to hardware and software tools. I have been a member of the AAVSO, I found out today, for 10 years and 2 days. I have my own observatory in the backyard and I know what the problems are. I'm at the same time one of the operators of the telescope network which the AAVSO is running. And I can feel how difficult it is sometimes to really control telescopes remotely, where you cannot go to the backyard to change things around or make sure things are not happening, but you solely depend on the remote functionality of your equipment. So let me start. And I apologize for these animations here, but I thought it might be one time when PowerPoint presentations with animations might be useful. So let's think about what we want to achieve in a system which we want to automate and remotely control. There are several use cases. If you want, think about you have an observatory which gets hot in summer and you want to switch on a fan. Very simple. You have sensors there, you have a thermometer, and at some point you reach a threshold and you want to use a fan to cool down things. So we have sensors, we have actuators, and somehow they need to communicate with one another. And you will have a unit which takes all these data measurements and distributes them to the actuators. Keep in mind, again, we could use cloud sensors, we could use relays as actuators. All sorts of things can happen and is very interesting to do in the background. What I have been using lately is something what is called a network protocol, which is called MQTT. Long word, it's messaging, queuing, telemetry, transport. It is actually a very nice publish and subscribe network model that makes it possible, that allows small devices like Arduinos to talk to one another in an easy way without too much overhead. It has a very small footprint as what code is concerned. So in the MQTT talk, you call something what the sensors are sending out, you're publishing a topic. And then you have other embedded controllers, for example, who can subscribe to those topics. And all that is distributed by these MQTT brokers, which is another item in this little network. But then if you have all these data, you might like to put them into a database. And there are lots of tools around, they're all open source. There is InfluxDB has become pretty well known lately, and Grafana. InfluxDB, as the name says, is a database. Grafana is a visualization tool which allows you to send out alarms and alerts at the same time. And I have been using for prototyping something what's called Node-RED. And I would like to show you a little bit about this one later on. Now, all these MQTT broker pieces of software, Node-RED, InfluxDB, and Grafana, they all fit onto a Raspberry Pi. I'm not sure if we have mentioned the Raspberry Pi before. Arduinos, Raspberry Pis, they work very well together, are relatively low cost. The embedded controllers I would like to introduce to you are even less expensive than the Arduinos, and they have Wi-Fi capabilities. So at some point, we even want to utilize web services. For example, we could go and find weather reports, weather forecasts, which we could utilize, or we want to send out emails as alerts or SMS messages. All this is possible, literally on your desktop or in your backyard. The controllers, embedded controllers for sensors and actuators controls, as I mentioned before, I would like to introduce you to some which are made by a Chinese company called Espressive. They are here ESP8266, very well known in the hacker community, and they provide Wi-Fi connectivity, and the ESP32, which is sort of the follow-up of that smaller device, and that has actually Wi-Fi and Bluetooth and is a dual core model. They're very inexpensive. The ESP8266 you can get for about $2 to $3. The ESP32 maybe double the price. And you can get whole lots of 10, for example, if you are a little patient from China. Alibaba is a very good source for those. And you get 10 for about $20, which I saw yesterday. And it's a ridiculously low price. You can distribute them in your backyard or somewhere else in the observatory, and you can make a little Wi-Fi network with those. So I would like to show you a few things, what you can do with them. Very important here is over-the-air programming. So instead of having a USB connection or an Ethernet connection or something like this, you can do everything wirelessly. So your new firmware which you're developing, you can distribute over the air. If you have one of these little devices at a place which you cannot get to easily, maybe under your roof or in a very far corner in your observatory, those are devices to get, and over the air will help you just to update the firmware. I mentioned already the Raspberry Pis. They have Wi-Fi capabilities. And instead of, like in the olden days, where you use all sorts of software which you have to download first to your Raspberry Pi manually, we use now container solutions. And one is, for example, Docker. You can look this up on the web. There are people who are already doing a lot of things for you. You can download those containers which contain all these software packages already. It's very useful if you want to work fast and if you want to update those packages. And they come with maybe 20 different pieces of software, and you don't need to do that manually anymore. Important too is you can run the Raspberry Pi without connecting a monitor or a keyboard to it in what is called headless operation. You use a web browser, you hook up, log on to this, and then you can use the keyboard on your laptop, for example, and operate your Raspberry Pi. Here are two pictures. On the left is the ESP8266. You see it's pretty small. And the silverish thing there in the bigger chip is what makes the heart of that development kit, what it actually is. Those kits are very useful because they typically provide USB connection, which is the first time you program these. It's very important, and it supplies power as well. Raspberry Pi 4 is now the version 4 on the right side. They provide USB connectivity, Ethernet connections, they have monitor connections, etc., etc. Very powerful these days, and you actually can build your own little PC if you wanted to. Here is something, and I don't want to repeat what Alan has already shown. The sensors, I call them here the feelers. There are lots of possibilities. We can look for rain, we can look for clouds, we can look for, if you are interested in the weather, for relative humidity and pressure. You can think about positions and orientations of the telescope itself. Sometimes as a safety precaution, we don't want to run with our instrument into some obstacles. We can look for the ambient light, and we can, if we have a setup where we move around with our mount, we can put a GPS unit on. And all these are our sensors which we can use in our environment. A few pictures here on top is the infrared sensor to look at the clouds working at 10 microns. The rain sensor, I had used the same rain sensor as Alan showed before. Then there are very good temperature and relative humidity sensors around, which are already enclosed, which is quite important, because if you put your instruments into the elements, it's a very different story if you do something on a breadboard or if you put them out into the weather conditions. Here in the Northeast, we have pretty hot and humid summers and very cool winters. The instruments have to be protected quite well. So it's good if you can find those already assembled.
You have about 2 minutes.
Okay, here are some actuators, the muscles, relays, we can drive those. We can use LEDs as indicators, or maybe for our flat panel illumination. We can use fans, or we can use, for example, motors. Here is a little one. If you look on the bottom of this picture, there are a couple of stepper motors, and you can build your own focusing devices with those to do autofocus on your telescope. I will just show you a few pictures of Node-RED. Node-RED is an environment which is what is called a flow-based development. It's a low-code development tool as well. You don't write now single lines of codes, but you use, for example, these rectangular nodes, and you have to define, if you double click on those, what these nodes are supposed to do. There is what you see here. The air temperature C is actually an MQTT input node, and it takes the data, and you can connect now other gauges, graphs, icons to that node, and it provides the message. And if you look here at the left side, you see what one of those messages is. Here is the ESP. BME280 is the type of a sensor I use. It's the Bosch sensor, which provides environmental temperature, humidity, and pressure values. And it provides, this is what MQTT uses as a topic. And it gives that message. And if you open these different objects here and the payloads here, you see actually a temperature. And this is the message which will be given through these wires to the gauges or the graphs. Here, briefly, I did something with, on the top left, you see here an ESP8266 with the environmental sensor, and I call this a sourdough breeder experiment. Like everybody else, I was baking more than usual during the COVID-19 phase, and my sourdough didn't develop too well. So I used one of these nodes, these little ESP8266 plus the sensor nodes, and put them into an icebox, put a light source in there. It's an incandescent lamp, which can be switched on and off. And now I can regulate my temperature, and you see on the bottom one of those regulated temperature curves, and I elevated the temperature, and now my sourdough is actually working much better than before. Now here's something that's a little more serious. Here is where you can see a display of the air temperature, the air humidity, and the air pressure. Coming back to the weather box and the sensors for cloud, rain, etc. Here is something what I wanted to show to you, what we can use. It's a fritzing design. Fritzing is a piece of software which allows you to make these drawings. It's very helpful if you use breadboards, for example, and you want to wire things together. Sometimes it's easier just to make these drawings first, because before you start to solder. That piece of software allows you to make these schematics. It actually provides PCB layouts without routers, and it provides a BOM. Very useful if you want to share things later on. Here are a couple of pictures of what I have in my backyard. Here is a very different footprint than what Alan had before for his weather box. And you can see here the rain sensor, of course. Here is the tip of the infrared sensor, which is looking towards the sky. Here is my temperature and humidity pressures, it's a temperature and humidity sensor. And I made an experiment, the rain simulation experiment. So I borrowed a spritz bottle here from my wife. And because we don't get rain right now for about 2 weeks, spritzed some water onto the rain sensor. And you can see here on the right side, if you get the software correct, that I have certain rainfall simulated during the period of 30 seconds where I update now the values. So this is very useful if I look for rain. Here is now the...
Over time, so you might want to wrap it up pretty soon.
Okay, I will. It's just almost the last slide. Here's the sky temperature displayed. Then I have the air temperature, the ambient temperature, and the ambient humidity. And then I call something here the MLX temperature, which is the temperature sensor which is built onto that infrared little sensor module. It gives you the temperature of the PCB. And for me, it was interesting to see how close that temperature is to the air temperature, which was measured independently. And I can just report they are pretty close together. It's about a 2-degree difference, which doesn't make a lot of difference if you want to compare now the sky temperature to the ambient temperature, because that is what we are interested in. This is what I do with what I call computations. And here's where it becomes interesting. On the top, I have all the temperature, the 3 different temperatures which I'm measuring displayed in blue. On the top is the sky temperature. On the bottom area, I have the difference temperature between the ambient temperatures and the sky. And that is where I can put thresholds on now to determine, let's say I have a temperature difference of 17 degrees Celsius. This gives me an indication of if there are clouds or not. Now if I put little LED, everything in software, in red and in green here, if the conditions are fine for clear sky, it's green, and if it's red, then it's cloudy. So this is what I wanted to show to you. There are lots of tools around which we can utilize for free. As amateurs, as more people who want to be a little more serious about automation. And I have a whole slew of lists, a list here of links which can be used, and I think we can make those available later on. Thank you very much.
Thanks, Helmar. Tom, why don't we move on to you and observatories.
That sounds good. Let me go ahead and share my screen real quick so everybody can see it. Looks like we have a little bit of latency here on the controls. There we go. Everybody see that okay? I mean, hope you can. Hope you can hear me fine. Good day to everybody. My name is Tom Smith, and I operate the Dark Ridge Observatory. Dark Ridge Observatory was one of the components that developed the APAS database. I put together all the hardware and ran the systems. But my observatory is in the Sacramento Mountains in the central south of New Mexico. I'm in an elevation of a little over 7,000 feet, and that nice Princeton telescope you saw at the first screen that Alan showed, that's about 8 miles away from me as a bird flies. And it's a real nice area. Good seeing that type of stuff most of the time. We're in the middle of monsoons now, but it's going away. So observatories. Why would you want to have an observatory? Well, observatories can do an awful lot for you. And I'm going to truncate a lot of this so that we can get through it quite quickly because we're running out of time. Well, one of the biggest things about observatories is you've got instant access to a scope or equipment that you can put on the sky. Oftentimes when you drag stuff out and put it back away, you can damage equipment, so you need to be concerned about that. And then there's always, once you get the equipment out and set up, you have to do alignments, photo alignments, so that you can take either astrophotography or do science photometry, spectroscopy in a much better fashion. And you certainly don't need to have great polar alignment if you're just going to go out and do some visual looking or that type of stuff. So having an observatory of a kind makes it much easier. You just jump out and you're on the sky. It's quite nice. So here's a couple of items here. Now, I'm not going to go into great detail on a lot of these. I've got a full series of YouTube videos that I'm sharing with the AVSO that go over soup to nuts, basically, for building a remote and a robotic observatory system, and that will be shareable for you. But basically, here's some of the things that you need to consider. You know, the where, the how, and the what ifs. The what ifs are really, really key here. If you're going to have an observatory, you got to know where it's going to be located. I mean, you will. It's either going to be close to your home in your backyard, or it's going to be located at some remote distance. And each of those have both their strengths and also their issues to deal with, the challenges. We won't call them issues, we'll call them challenges, because you can have a lot of fun with a remote observatory too. And a remote observatory in your backyard isn't that far away from being a robotic observatory 10,000 miles away. So, you know, it's just a matter of looking at a few things differently. One of the things you need to make sure you've got for our equipment anyways, you need to make sure there's power available. Many ways to do that. You can have the mains system if it's available with a backup system, battery if you want, a solar implementation, which is really nice to have. And also the hybrid model allows you to utilize both those. One thing that's very important, at least in my opinion, is an uninterruptible power supply, UPS. This will give you a little bit of chance to handle some of those short duration outages where you can take the actions you need to put your observatory and equipment in a safe condition, assuming you can. Grounding, obviously very important throughout. That's for your safety as well as the equipment's. I want to highlight your safety here. We're dealing with mains power in many cases, so it's important to realize what you can and can't do there. So control of the observatory, that's very, very important, and the equipment in it. You got to make a few decisions about how you're going to do this. If you're not going to have a remotely robotic observatory or even a remotely operated observatory, it's great. You can just get your observatory opened up, get out and start taking your pictures, do what you want to do there, take your science data. But I like to sleep, as it shows you in the bottom drawing. I do operate everything as much as possible in a robotic mode. And that's after you've shaken it out in a remote operation. So can you reach this telescope and equipment? That's important to be able to do that. You know, if it's in your backyard, it's great. You've got probably your local area network, your LAN that you can handle. But if you're going to send it across the internet and deal with that type of stuff, you need to have a little bit more thought about security and your physical components, where they're going to be located, how they're going to operate. I've got a couple of items here listed. Security cameras are really, really important in my opinion. And if you've got nice cameras, it's great to be able to have two-way audio. So you can hear your equipment move, you can hear what it's doing, those bleeps and beeps. As well, it makes it quite convenient if you need to do some adjustments. You can have a second person out there working on your equipment and your audio can go back to them through camera or another mechanism, another way to do that. But audio is very important too. Certainly not as big as having visual indication of what's going on, but it can help a lot. You got to think about locks and fencing if you're going to be a remote. That's really important. Potential failures of hardware. We'll talk more about this when we talk about what if, so let's just skip on a little bit here. Getting access to your computer over the internet is important, but you need to take some more of these controls or think about what you would do in those instances where things go wrong. How are you going to do this? How are you going to build yourself an observatory? Don't get scared off. First off, an observatory can be anything you want it to be. It's just a real nice way to go out and get busy on the sky without having to waste additional time trying to set up. But here's the things you can think about. a dome, a clamshell, a roll-off roof, which is common, a roll-off building, which is common too, a flip-off structure, or how about just as Richard Berry said at the beginning, a tarp over your scope. That is an observatory. It means you can get out there on it, and provided you don't have extreme weather conditions, then that's totally acceptable. Of course, it's nice to be able to go out and either sit down in a place and enjoy it in a enclosed environment, or remotely operate from the comfort of your own house. So here's some notes on those. One of the things that really is important is that very first top part, where it says a dome sounds sexy, but sometimes it's more of a headache than needed. And it's very true. When you go up and down the road here where I live, you can see observatory domes all over the mountains, speckling the mountains. And they're just a real security risk. I mean, you know, it just says to people, you got a great amount of equipment and money tied up there probably. But it doesn't have to be that way. In fact, my observatories are all roll-off looking sheds. You wouldn't even know that there was an observatory there if you didn't know what rails were. So anyway, you can build an observatory out of about anything. If you're going to modify some kind of a structure that it's pre-built, I've seen quite a few people use, for example, those Rubbermaid storage sheds, and they'll modify them to be like a roll-off building, which is great. They work good, but you do have to take into account that they were designed for a particular structure and a structural load. So you need to beef that up a little bit when you do that. Tip-off shelters are pretty easy. You can go out and just tip your observatory roof off yourself if it's a small one and get to observing. But you need to then be able to go out and close it. And unless it's motorized, then you're going to have to go out and close it if you get inclement weather coming in. And these weather stations that are being developed, they're quite easy to build. There's really not a lot to them, but they're key. They're key to know that your equipment's going to be safe where it is, especially in remote and robotic operations. Here's a couple of different kinds of observatories, just some pictures that show you different things. The classic roll-off in the upper left, and that one has a south dropping wall, so you can go farther down to the south if you want to. You can see there's complex observatories, there's very simple observatories. You can do whatever you want, make it as fun and interesting as you need to for your particular science projects. So how are you going to get it built? Who's going to do it? Are you going to do it? I mean, I love doing DIY stuff myself. I build everything out here myself. The hardware, the software, the building structures, the infrastructure, all of that type of stuff. But there's a couple of things to think about. What are you going to make it out of? Well, wood is pretty classic. I mean, it's traditional. People build observatories out of wood. And you saw a real nice wooden structure that Princeton 32 that went over to Dave Middleman's location. You can see that construction is very common. However, in our location here, I get a lot of high temperature changes and humidity swings, and that wood tends to warp even if you've got it preserved pretty good. You can construct an observatory out of just a simple steel frame if you've got the capabilities to do welding or bolting if you need to. And then there's those plastic molded structures that work really good. They sometimes discolor over a period of time, and often with the UV, especially up here at 7,000 feet, some of that plastic component can be damaged quite a bit. Well, one thing I want to back up and talk about real quick is that was, we said grounding earlier. Down at the bottom of those plastic or molded type observatories, often they can build up a static charge. So if you modify one to use it, make sure you take into account your grounding. Your equipment will like you better. So here's what you got to worry about. Who's going to do it? You're going to do it yourself. If you do, remember you've got oftentimes an HOA. I don't have them here. My nearest neighbor's over a mile away. But if you do have somebody do it for you, are they reputable and licensed? You need to make sure they are to make sure you get the best quality and what you really want to have in your observatory. If you're going to pour concrete, you need to make sure your trucks can get there. My driveway is a half mile long and it's got a hairpin switchback in it, yet I still have been able to get concrete trucks up, but you need to think about that. And permits, yes, you need to check with your local building permitting department to make sure you're in compliance with that if you're going to build an observatory, especially if it has mains power to it and that type of stuff. And here's what's really kind of important, the what ifs. You got to sit down and you got to think about what possibly could go wrong with your observatory, even if it's just in your own backyard. Make a list. Start thinking about stuff that could cause equipment damage or you know, just plain loss of connectivity, for example. How are you going to protect your equipment in a loss of power or connectivity? How are you going to take care of that? Oftentimes, folks set up a watchdog type internet service or local area network service that sort of pings your main system to make sure that you've got connectivity back and forth. And if not, over a period of time, it can oftentimes reboot your router or whatever your other issues are with your particular connectivity. And so, you know, yeah, Murphy's going to get in your way. That's a fact. You're going to have problems. And even if you sit down and take copious notes, you're going to miss some things. And that's all part of the fun too, is learning what you didn't know, because you won't know what you don't know. That's a fact. Anyway, those are the kinds of things you need to take a look at. Loss of power and multiple things happening all at one time. If you know somebody in the area, it's great. It helps a lot. You can collaborate with them in a lot of ways. If it's a remote observatory, especially if it's an area where it's susceptible to vandalism or, you know, theft or damage, it's a good idea to meet your local law enforcement and your fire folks. Take them up to your observatory, show them what you got. Let them see how interesting astronomy can be, and just, you know, stay in touch with them. And if you know somebody in the area that's got skills that can help you out on a remote system, meet them, talk to them, get involved with them. Even if it's just they go out and just close your roofs or something if you need to in a big weather storm when you've lost power and your internet connectivity. Oftentimes someone can get out there and just close it up and make it safe enough until you can repair it. So it's good to have that capability.
2 minutes, Tim.
That list thing. Go ahead. 2 minutes? Okay, so here's that list thing. Make a detailed list. Sit down and think about things that can go wrong, and then write down what you think you might be able to do to mitigate those things. And definitely think way out of the box, because you never know what's going to happen. Again, there's much more details. I've got about a 10 or 12 series videos set up on YouTube, and those will be available through the AVSO also. But with that, I want to say, so now get out there and start building it. And remember, you don't have to spend a ton of money. It doesn't have to be anything really fancy. It could be as simple or as complex as you wish to make it. And remember that things always grow. So get out there and enjoy it. Have a good time. Pleasurable observation settings. Thanks, you guys, for listening. I appreciate it. That's it.
Thanks very much, Tom. And thanks again to all of our speakers this session. We have a few minutes, so why don't we just jump straight into Q&A. So the first question that we have is Molly, and I guess Phil wants to weigh on it as well. When do you use check stars, and when do you only use comp stars?
So not gonna lie, I've not figured out how to use check stars in VPhoto. I couldn't really find much on them in the manual. So I just use comp stars, and I delete ones where the magnitude that was measured is too far from the actual known magnitude of that star. I just take those out so that it doesn't make an anomalous measurement. So yeah, I'm still kind of new at this. So yeah, I don't know. I've not used check stars.
Well, I take that, if you're using only a single comp star, you should always use check star. The check chart allows you to make sure that the comp star isn't varying or that the atmosphere isn't varying. So a single comp star is, you just have to use a check star. It also allows you to give a measure of uncertainty if you're doing a time series. But yes, you got to use a check star if you're using only a single comp. And you can do that in Molly. You can do it in VPhoto. you can specify any of the stars in the AVSO comp series by just clicking on it. It brings up a box in VPhoto, and you can change that star to a check star. Try it.
What's the difference between a check star and a comp star?
A comp star, well, is a star up against which you are measuring the variable. A check star is not used in the analysis of the variable's magnitude. It's used as a way of making sure that nothing else is varying in the sequence if you're using an ensemble.
So it's like a comp star for the comp star.
It's sort of, yeah.
Okay.
You can use the measurement of the comp star versus the check star just to make sure that all your comp stars are behaving.
Yeah, I'll try that out on my next submission.
Yeah.
We have a DSLR, a DSLR related question. This one says, if you're using a DSLR camera and you don't have any photometric filters, what channel is the best for variable star / exoplanet photometry? They actually suggest is R the best channel. And I'm pretty sure the answer to that is no. But I believe the best channel is G. George, I think you would be good to answer this, or Richard?
I could step in. You definitely want to use the TG channel from a DSLR. That has the closest match to the Johnson's V. Red is way too wide. It's very problematic to use that. So G is the best.
Yeah, and I've been doing some experimentation using Bayer filtered cameras bin 2x2, which basically puts together the R, G, G, and B filters. And I'll be reporting on that briefly next week at the CMOS. But basically, if you bin Bayer material, you get something that's quite close to TG.
I want to add real quick that Barbara Harris, who's a prolific AAVSO observer, she uses a DSLR, and she's going to be giving a presentation on the Astro Imaging channel on October 18th about how to do photometry and how to do variable star observing with the DSLR. So for folks who have DSLRs, tune into the Astro Imaging channel at 9:30 p.m. Eastern time on October 18th to see Barbara's talk about how to do it.
Our next question is for Tom. Actually, let's, that one seems a little bit more tongue-in-cheek, so maybe we should go to one that's a little bit more serious for now. What is the, so someone has a question about flat field illumination. They say that they have bought an electroluminescent panel for flat field imaging, but that their uniform illumination is still bigger than 1%. Is it possible to use it even if it's above 1%, or do they need to find something else? And this is probably a question for one of the makers, Alan. I think you're muted, Alan. Oh,
Yes.
there you
So
go.
you're going to, all flat panels have some limitation on the uniformity, and I think 1% is actually pretty reasonable. Some of the photometrists may have some. There may be techniques for, improving upon that, but I think 1% is pretty good. And if it's 10%, it's much more difficult. But Gary Walker, who's somewhere online, or some of the other more experienced photometrists that do flat fields, either with panels or twilight flats, might be able to add more detail.
I agree, Alan, that I think 1% is pretty good. I don't know if you're going to find a flat electrolucent panel that gives you better than 1%.
Yeah, and depending on the geometry of the situation, you can put a diffuser of some kind close up to the optical system on the DSLR, so as to diffuse the image of the already diffused source. There's a fair amount of this is going to depend on the focal length of the lens on the DSLR and so forth. But on the whole, I would say that 1% is not bad.
Okay. So this question really is for Tom. I have a feeling that you're going to have to ballpark this quite a bit, but the question is, approximately how much would it cost to build a slide roof observatory that's 10 feet by 10 feet?
Yeah, I just typed an answer in there for the person that asked, but that's okay. Let me give you my answer. Like Arnie Hendon always says, it depends, and it really does depend on what you want to do with that 10-foot. I was able to construct a couple of small 8-foot by 8-foot observatories in my quote-unquote backyard, quarter mile away from me over there, for under around $500 for the structure. And it really only took a little while to do that. The hardest and not the hardest, but the longest part of that was building the pier. I had to dig, and I have nothing but rocks up here. So it can go anywhere from $400 or $500 up to it's astronomical in prices. You can go anywhere you want, and I don't mean to be tongue-in-cheek with that, but it's absolutely true. If you want to make this thing totally robotic, automatic, don't touch things, fully integrated, you can spend upwards of $10,000, $12,000 on just your observatory itself. But you don't have to do that. You can put yourself a Harbor Freight tarp over the top of your telescope to start with if you want. Go from there. See if you enjoy doing that kind of science work in your backyard. Hope that answered.
Cool, thanks. So this next question is probably going to be a little bit of a debate, but I think it's worth asking. It says the various Johnson-Cousins filters look very much like the response of many color CMOS cameras. Why not use a color CMOS camera and then select a given channel to correspond with either B, G, or R? And then those will be reported as the various colors. So there are a couple of reasons to or not to do that. I think, will you be talking about this a little bit next week, Richard?
Well, these the photometric filters and Sloan and whatnot, they have a standard wave band, whereas the color filters on a CMOS camera or any color camera are not standard, and they cover a different part of the spectrum than the photometric filters. So you could be getting more of a different wavelength of light in that filter than the standard. So when you go and report that there's that the magnitude of the star is this in V band, that's going to be slightly different if you use the G filter off of your DSLR or a G filter on a monochrome camera. They're not the same. I mean, they look similar, but they cover different parts of the spectrum, and the photometric filters are a standard that is known. That way the measurements can be compared to each other more reliably.
Yeah, the problems really seem to come with red stars, because first of all, the color filters on the Bayer systems vary from maker to maker. What they do is they say, well, we'll just put on a stable dye that won't decay. And then we'll use software to transform the colors so that human flesh looks like human flesh and trees look like trees and the sky is blue. You could do that if you wanted to spend your life figuring out how to transform stars into standard magnitudes. Or you can say, well, and this is what I've been experimenting with, is to cram them all together, figure out how bad the deviations are, and then work on stars that are not red. And this takes us back to what Phil was saying. Is, yeah, you can use a green filter, and it's a reasonable approximation of V, and it can be transformed pretty easily into V.
Tim, did you want to say something?
Yes, I do. Now, I think with the issue with the DSLRs, don't they use an infrared filter that may or may not be in an astronomy CMOS camera? Is that correct?
They have a spectrum filter that cuts out a lot of the red spectrum and all the IR and UV.
Yeah, the DSLR ones do. I know that, but
Yes,
what about the astronomy CMOS?
Oh yeah, a lot of astronomy CCD cameras don't have the UV IR cut filter, and you have to put one in your optics train.
Right, and the problem is you don't know whether it has that IR cut filter either.
So
usually
really,
you do, because you need to put one in your train if it doesn't have one, and it'll be pretty obvious if you're using a refractor, for example, and you get these bloats around the stars.
Big bloated, yes.
Yeah.
Yeah, in a refractor you will know, right?
Yes. Yeah, and I think that's published usually with the description of the camera, or if not, the people on forums will tell you whether it has one built in or not.
so it's really the variability among color CMOS that's the issue. That they go it's this all over the place when it comes to what color channels, what colors make it through what channel.
Yeah, now I understand that there are ways to transform those, but I think you have to do some measurements. I don't really know what all is involved. I'm hoping Barbara covers some of that in her talk, but because I know people do DSLR photometry. You just have to either transform it or submit it you can't say that it's V, because it's not. Not that you can't do photometry with a DSLR, but you have to do some extra stuff.
Yeah, I mean, it would not be too difficult to work up a standard protocol for take a picture of this area, which has a wide variety of stars, especially a lot of extra red stars. Do the photometry based with whatever camera you have, and then determine whether or not you can do good photometry and what is the best way to do that. In other words, take a completely wild animal and try to tame it.
So one issue that I see with DSLR is that if you just want to take your own photometry and compare it to your own other photometry that you do, it's likely fine. You can probably get good results, especially because you can, do differential photometry and not necessarily care about standardizing it, so to speak. But if you want to submit it with respect to other people, then you really need to care about exactly what that value is. And one thing that's just never been clear to me is that from camera to camera, how close is TG, TR, and TB? You are using one DSLR versus another, are the response curves the same for each of those different types of pixels? And that's something that I've never gotten a good answer to. And that even if they're close, it could cause some problems when you try to compare from observer to observer, which is one thing to worry about with DSLR. But it just kind of depends a little bit.
And exactly the same problems exactly the same arguments with one-shot color cameras. The company that manufactures the chip is not trying to do astronomy. They're trying to make pretty pictures of one kind or another. And basically, we're only coming up to a time when, because as CCDs get harder to find, we're now coming up to finding that these inexpensive Bayer cameras and inexpensive, well, basically DSLRs too, or inexpensive Bayer cameras, how to use those optimally. And the answer is, as Bert sort of indicated, is we really don't know the best way to use these things yet. There's experimental work to be done.
Okay, and with that, we didn't get to quite all of the questions, but we did do quite a few of them. If you still have a question, please feel free to ask it on the Site and Equipment Forum. People will be more than willing to answer. And we want to thank everyone again for coming and visiting the webinar. We have one that is CMOS specific next week, so if you're really wanting to know more about that, please tune in. It's been a very hot topic recently, and it's going to be moving forward, whether we want it to be or not. Thank you again to all of our speakers for taking time out of their day to do this. And thanks again to our sponsors, Voice Astro and Attic Cameras. And as always, this webinar will be published on our YouTube channel in the week following. Thanks again, everyone, for attending, and have a great rest of your day.
Thank you.
Thank you.
Bye-bye.